This is a GRIDeoS on multiscale topology optimization. Usually in engineering, we wish for materials and structures with objectives, with properties that are not always compatible. For instance, we want something that is light, but at the same time is stiff and with a high performance. This is usually done analyzing some functions, some specific functions. Some of them that are more common involve some kind of energy revolving around the body. For instance, the compliance, which is basically the work performed by the applied load, or something that is close in terms of definition, which is the elastic energy of the body. This is true for a spring, but it's also true for some kind of continuous body, something more complex. A common strategy to connect, to analyze these functions, these energies, is through a principle where in equilibrium the displacement field is basically the one that minimizes the potential energy. In this sense, we can tackle the problem through, for instance, the minimization of the strain energy involved in the body, or minimizing the compliance, or connecting both of them, maximizing the potential energy in equilibrium. Usually this is done taking the base problem, using the compliance in a finite element formulation, as is shown in this slide. This is usually programmed using a specific variable, which is the raw. Basically, it's a variable that says that in each point, in this case in each finite element, we have a density. It's a virtual density that tells us that there is or there is not material. What we wish to do is to distribute the material within a domain using a given restriction, a volume restriction or a weight restriction, for instance, saying that in the end I must have a given quantity of material distributed in a way that makes the structure as stiff as possible. Usually what we also do is to take this variable and to penalize it, because what we wish is to not have any kind of intermediate value. We wish either no material, void, which is raw equal to 0, or dense material, black, raw equal to 1. Basically what controls the process are the derivatives. If we take the derivative of the stiffness or the derivative of the objective function, what we have is the equations that we show here. In this case, how does it happen? If we have an initial distribution, as we can see in the example with the springs, we test it, we can see that there are two springs which basically don't deform, they're just moving, and the other ones deform. What the derivative tells us is that it's better for the objective to have more material there because of the minus. The minimization makes it better to have more material in the ones that effectively give a response to the boundary conditions, to the load. What happens here is that in the next step we have more material where it's needed and less material where it's not needed. If we take a general problem, what can we do? We can basically say that we're using some kind of isotropic material and we're controlling how the material is distributed using the variable that we spoke about before. We can use the function that we talked about before. Essentially, what we can do is to try and see what's the distribution. In this case, what we have, we get to a point where we have material in the best regions and no material where it's not needed or where it's less needed. This then becomes something that's more or less like what's represented, where we have material and void. We can get to the best solution possible, to the best structure possible for a given objective, in this case, for better stiffness. If we add up to this some kind of control over the material itself, we can get some kind of homogenization procedure and connect it, and we get to a point where we can act not only upon the structure, but also upon the material that is used to build the structure. In this case, what we have, we have the variables that control the problem, but instead of only having material and no material, we have material at a given point, which has the constitution that's defined by a specific optimization problem. As we can see above, we have a new problem, which is the problem of the microscale. In the end, what we get is a hierarchical optimization procedure where we have optimization on the macro scale and optimization on the micro scale. In this case, we can get to a point where we have, in each point of the structure, we have the best material possible for that point in the structure. So it's constantly varying along the structure. We can have it with material in void, in cellular materials, or we can have it with two materials of different properties or more materials of different properties, as in composite materials. We can even do this separated. In this case, what we can do is to study the material isolated without regarding the macro scale, without regarding the overall structure. So for a given option, for a given objective, we can get the best material possible to answer a given requirement. Once again, either for material in void, which is something like this, or composite materials with different constituents. All of this can be extended, and we have lots of options to work with. For instance, we have the base problem, where we get material in void only in the macro scale, or we can have another option where we can get one material and another material, different materials without void in the macro scale. We can also do the same thing, but instead of having an isotropic material, we can have some kind of different material, a composite material, for instance, and we optimize the macro scale, the structure, using a specific anisotropic material. We can also do the same over the material itself. We can do the macro scale optimization and the micro scale optimization, where in the macro scale we have the best structure of material and void, and the material used in that macro scale is the best material property, the best material distribution that's optimized at the same time. The most complex and the most complete option on this level is the hierarchical option, where what we do is to have an optimization problem over the material for each point of the macro scale. And in this case, we have macro scale optimization and micro scale optimization, always connected, always coupled. We can have an intermediate problem where we can say, as is usual in composite materials, in structures made of composite materials, where for each region of the macro scale of the structure, we try to find the best material distribution, the best material orientation for that given distribution or for that given region. And this is the case for the intermediate one. We can even do another thing, which is on the limit, the lower limit, we have only one region, and we study the macro scale, but we do the optimization on the micro scale level. How does that lead us to results and to the programming part and to the software? Here's some examples. First of all, the typical topology optimization. In this case, we have examples of, for instance, a multi-objective optimization where we have on one extreme, we have a mechanical problem, and the other objective is a thermal conduction problem. And we can see the variation in terms of weights of each one of the problems. We have here another option, another example, once again, mechanical and thermal. And we can see the different influences both in 2D and in 3D. Here another example, in this case with a multi-load case, which is basically a multi-objective optimization, but the two objectives are of the same nature. They're both load cases. And now, the same thing but without an isotropic material, using some kind of composite material for the micro scale. Here we can see the influence of that micro scale, both in terms of the distribution and in terms of the relation between the properties of each one of the constituents. And here another example, which is easier to see what is the main objective. We take the micro scale and we orient it in different alignments. Another example, in this case for hierarchical optimization, where we can get to a point where we have different microscales for each one of the points of the macro scale. Here are examples, simple examples, where we can see with different parameters of optimization the microscales for each one of the points. Here the same thing, but instead of using square microscales, we use representative units. There are hexagons, which is different. And here another example, where we take the purely mechanical problem with some examples of optimal microscales. And we do basically a multi-objective optimization, where we gradually impose more and more of the thermal problem. Here we have a 3D case, just as an example. In this case, what we have is one microscale for the whole case, and we oscillate between each one of the macro scale problems that you see, both in terms of isolated solutions and in terms of multi-load solutions. In this case, we have a specific microscale for each one of the parts of the I-beam, which gives different results. And finally, we take an example where we take a high-performance car, a competition car, and use a specific component to study. In this case, the supports of the wing, the back wing. And we optimize it. We optimize it both in terms of macro scale and micro scale, or different options in terms of the ideal material distribution for that solution.